Problem 7 asks us to take the limit as x goes to 0 from the right of cosecant raised to the sine x. So if I try to plug 0 into these functions, cosecant of 0, the limit of that, it's actually going to approach positive infinity as you get towards 0, because there's actually a vertical asymptote there on the graph. But sine of 0 is 0. So this is actually infinity raised to a 0 situation. Also notice that the expressions had x in the base, right, and x in the exponent. So this is where our natural log can help us out. So the first thing I'm going to assume is we're going to say, well, let's just imagine that the limit does in fact exist, and it's just some value L we haven't found yet. So now I'm allowed to take the natural log of both sides. And it doesn't matter if I take the natural log on the outside of the limit, I'm actually allowed to move it inside of the limit. So I'm allowed to say, well, this is the same thing as the natural log of cosecant x raised to the sine x, and that's going to equal the natural log of L. So now what I'm going to do is I'm going to work with the left side of this equation and figure it out as far as I can, and then when we get this as far as we can go, we'll set it equal to this and then solve for L. Because remember, the limit here, L, right, is the goal. So just finishing the limit is not going to be good enough here. So now I'm going to use my properties of limits, or logs, excuse me, and I'm going to pull the sine x down front. If I try to evaluate now, I'm at a 0 times infinity situation. So I'm still in an indeterminate form, right? But I'm still not quite where I need to be for L'Hopital. So I can move one of these expressions into the denominator. And so since sine of x has a reciprocal identity, that's pretty easy. For the same reason we didn't move natural log before, I'm just going to move this sine of x into the denominator. So ln cosecant of x stays in the numerator. The denominator is now going to be cosecant x, because 1 over cosecant is in fact sine. Now if I look at these limits, I'm in an infinity over infinity situation. Now I can use L'Hopital. So we're going to take the derivative of the numerator, and the derivative of the numerator says it's 1 over the stuff inside, this is cosecant x, right? 1 over the stuff inside the log, and then you multiply by the derivative of what was inside. And the derivative of cosecant is negative cosecant cotangent. So that's just the derivative of this. Then in the denominator, I take the derivative of cosecant, and I get negative cosecant cotangent x. So this is the same thing as saying all of this over 1, right? So I have a fraction in the numerator, a fraction in the denominator. So I can simplify this by multiplying the fraction on top by the reciprocal of what's on bottom. And I'll end up getting negative cosecant cotangent over cosecant, I keep trying to write cosine there, start it over, cosecant x times negative cosecant cotangent. Now the reason I didn't combine these cosecants is because look what happens. I can multiply this together. So this simplifies down to 1 over cosecant x. So I could evaluate this here because we've kind of already seen from all of the previous steps. I could stop here and say, well, this is really 1 over infinity, which is 0. If you didn't see that, you could have taken it back one more step and said, well, 1 over cosecant is sine, and sine of 0 is 0. So we get 0. But remember we said, well, we're not actually trying to finish the limit. We're trying to find L. So remember this guy back here? all we've done is said that this left side of the limit simplifies to 0. So now, we always have to do the last step of this problem when we use natural log. 0 is the natural log of L. To solve for L, well, we get rid of the natural log by raising both sides over e. So e to the 0 is 1, and e to the natural log cancels out. So this limit equaled 1. So it's a little kind of wild that this indeterminate form turns into this indeterminate form. Then we get it to this indeterminate form, and it all ends up being 1.